In recent years, a renaissance has been happening in AI, partly due to the hope raised by the success of new techniques such as deep learning, and partly due to the realization that the old problems cannot be sidestepped. To distinguish these types of research from the conventional works, new names have been introduced, including human level AI, artificial general intelligence, and smart AI. Strong AI. Some people also call this type of work strong AI, though it was not Searle's original meaning of the term. These new labels carry a common message, as AI no longer means what it used to mean within mainstream AI. A new brand is in need, even though what it refers to is not really new. Right. Now, artificial general intelligence could also be interpreted in this way. If a general purpose system is nothing but many special purpose systems combined together. However, many AGI researchers share the belief that general purpose systems and special purpose systems have certain fundamental differences that are qualitative, not quantitative. AGI research may produce results that look like the results of conventional AI, but they will be byproducts as the research is not aimed at domain specific solutions. Compared to the works under the names of human level AI and strong AI, the paths explored in the artificial general intelligence community are generally more unorthodox, since conventional AI is disproved here not because it has not moved far enough, but because it has been moving in a direction that is different from that of AGI. This dissatisfaction of mainstream AI is not enough to give AGI a common working definition. Actually, within the current AGI domain, the previous perspectives of AI can still be recognized. For instance, some projects attempt to achieve AGI by using an architecture that integrates various cognitive functions, while some others by following the single rational principle. Though the researchers on each side of this distinction still have different architectures and principles in mind. Now, some other definitions. So, description here is the working definition proposed in Wong. Intelligence is the capacity of an information processing system to adapt to its environment while operating with insufficient knowledge and resources. Since the working definition of a new concept must depend on some existing concepts, otherwise it would cause an infinite regression. In this definition, information processing system is used in a broad sense of the phrase to include all computer systems and robotic devices, as well as many animals, though it will not include everything such as rocks and rivers. Such a system can be described as being driven by some tasks or problems, though the system does not need to know or understand them consciously, and can carry out or solve them, at least some of them to certain degrees, by taking some actions. Now, the internal relations between the tasks and actions can be called the system's knowledge or beliefs. The system's information processing activities are basically to choose and carry out proper actions to accomplish the existing tasks. And these activities cost computational resources, mainly the time for computation and action, and the storage space for tasks and knowledge. Among all information processing systems, the above definition draws a line between the intelligent ones and the unintelligent ones according to two features that specify the system's working condition and its coping strategy. Here, with insufficient knowledge and resources, specifies the normal working condition. Let me highlight that. Insufficient knowledge and resources specifies the normal working condition of the system and is with respect to the concrete problems the system must deal with. In this context, having sufficient knowledge means the system knows the proper algorithm of solving the problem. Having sufficient resources means the system can afford the resources, chiefly time, required by this algorithm when applying it on the instances of the problem. On the contrary, with insufficient knowledge and resources can be further divided into three restrictions or requirements, that is, the system must be finite and open and operate in real time. Being finite means the system's information processing capability, such as how fast it can run and how much it can remember, is roughly a constant at any period of time. This requirement seems trivial as any concrete system is surely finite. However, to acknowledge the finite nature means the system should manage its own resources rather than merely spending them. This requirement is mainly for the theoretical models, since most traditional ones like the Turing machine completely ignore resource restrictions. Now, being open to new tasks means to make no restriction on the content of a task as long as it is expressed in an acceptable form. Every system surely has limitations in the signals its sensory motor mechanism can recognize, or the languages its linguistic competence can handle, but there cannot be any restriction on what it can be told or asked to do. Even if a new experience conflicts with its current beliefs or a new task is beyond its current capability, the system still should be able to handle them properly rather than simply ignore it or even be crushed by it. For the system to live and work in real time means the new tasks of various types may show up at any moment rather than come only when the system is idly waiting for them. It also means that every task has a response time restriction, which may be in the form of an absolute deadline or as a relatively expressed time pressure, such as soon as possible. In general, we can consider the utility of a solution to be a decreasing function of time. So, even a correct solution may become worthless when produced too late. A real time system must respond according to these restrictions, even when they cannot have been completely satisfied. Now, moving on. Uh, so, we can compare other definitions, and I'll move on to another research paper, right? So this is basically AI and the four seasons of AI. So AI is bringing the birth of AI. Although it is difficult to pinpoint, the roots of AI can probably be traced back to the 1940s, specifically 1942, when the American science fiction writer Isaac Asimov published his short story Runaround. The plot of Runaround, a story about a robot developed by the engineers Gregory Powell and Mike Donovan, evolves around the three laws of robotics. A robot may not injure a human being or through inaction allow a human being to come to harm. A robot must obey the orders given to it by human beings, except where such orders would conflict with the first law. And three, a robot must protect its own existence as long as such protection does not conflict with the first or second laws. So Asimov's work inspired generations of scientists in the field of robotics, AI, and computer science. Among others, the American cognitive scientist Marvin Minsky, who later co-founded the MIT AI laboratory. Marvin Minsky. So, at roughly the same time, but over 3,000 miles away, the English mathematician Alan Turing worked on much less fictional issues and developed a code-breaking machine called the bomb for the British government with the purpose of deciphering the Enigma code used by the German army. By the German army in the Second World War. The bomb, which was about 7 by 6 by 2 feet large and had a weight of about a ton, is generally considered the first working electromechanical computer. The powerful way in which the bomb was able to break the Enigma code, a task previously impossible to even the best human mathematicians, made Turing wonder about the intelligence of such machines. In 1950, he published his seminal article, Computing Machinery and Intelligence, where he described how to create intelligent machines and, in particular, how to test their intelligence. This Turing test is still considered today as a benchmark to identify the intelligence of an artificial system. If a human is interacting with another human and a machine and unable to distinguish the machine from the human, then the machine is said to be intelligent. The word artificial intelligence was then officially coined about 6 years later when in 1956, Marvin Minsky and John McCarthy, a computer scientist at Stanford, hosted the approximately 8-week-long Dartmouth Summer Research Project on AI, Artificial Intelligence, DSR-PAI, Dartmouth Summer Research Project on Artificial Intelligence, at Dartmouth College in New Hampshire. This workshop, which marks the beginning of AI Spring, was funded by the Rockefeller Foundation, reunited those who would later be considered as the founding fathers of AI. Participants included the computer scientist Nathaniel Rochester, who later designed the IBM 701, the first commercial scientific computer, and mathematician Claude Shannon, who founded information theory. The objective of Dartmouth Summer Research Project on Artificial Intelligence was to reunite researchers from various fields in order to create a new research area aimed at building machines able to simulate human intelligence. Then we had the AI Summer and Winter, the ups and the downs of AI. So the Dartmouth conference was followed by a period of nearly 2 decades that saw significant success in the field of AI. An early example is the famous ELIZA computer program created between 1964 and 1966 by Joseph Weizenbaum at MIT. So ELIZA was an NLP tool, natural language processing tool, able to simulate a conversation with a human, and one of the first programs capable of attempting to pass the aforementioned Turing test. Simulate a conversation with a human, and one of the first programs to capable enough to pass the aforementioned Turing test. Another success story of the early days of AI was the General Problem Solver program developed by Nobel Prize winner Herbert Simon and R&D Corporation scientists Cliff Shaw and Alan Newell that was able to automatically solve certain kind of simple problems like the Tars of Hanoi. As a result of these inspiring success stories, substantial funding was given to AI research, leading to more and more such projects. Right. In 1970, Marvin Minsky gave an interview to Life magazine in which he stated that a machine with the general intelligence of an average human being could be developed within 3 to 8 years. Yet, unfortunately, this was not the case. Only 3 years later, in 1973, the US Congress started to strongly criticize the high spending on AI research. In the same year, the British mathematician James Lighthill published a report commissioned by the British Science Research Council in which he questioned the optimistic outlook given by AI researchers. Lighthill stated that machines would only ever reach the level of an experienced amateur in games such as chess, and that common sense reasoning would always be beyond their abilities. In response, the British government ended support for AI research in all except 3 universities, Edinburgh, Sussex, and Essex, and the US government soon followed the British example. This period started the AI winter, and although the Japanese government began to heavily fund AI research in the 1980s, to which the US DARPA responded by a funding increase as well, no further advances were made in the following years. Then we have the AI fall, the harvest. So one reason for the initial lack of progress in the field of AI and the fact that reality fell back sharply relative to expectations lies in the specific way in which early systems such as ELIZA and the general problem solver tried to replicate human intelligence. Specifically, they were all expert systems, that is, collections of rules, which assumed that human intelligence can be formalized and reconstructed in a top-down approach as a series of if-then statements. Expert systems can perform impressively well in areas that lend themselves to such formalization. For example, IBM's Deep Blue chess playing program, which in 1997 was able to beat the world champion Garry Kasparov, and in the process proved one of the statements made by James Lighthill nearly 25 earlier wrong, is such an expert system. Deep Blue was reportedly able to process 200 million possible moves per second and to determine the optimal next move, looking 20 moves ahead through the use of a method called tree search. However, expert systems perform poorly in areas that do not lend themselves to such formalization. For example, an expert system cannot be easily trained to recognize faces or even to distinguish between a picture showing a muffin and one showing a chihuahua. For such tasks, it is necessary that a system is able to interpret external data correctly, to learn from such data, and to use those learnings to achieve specific goals and tasks through flexible adaptation, characteristics that define AI. Since expert systems do not possess these characteristics, they are technically speaking not true AI. Statistical methods for achieving true AI have been discussed as early as the 1940s when the Canadian psychologist Donald Hebb developed a theory of learning known as Hebbian learning, that is classical conditioning, that replicates the process of neurons in the human brain. This leads to the creation of research on artificial neural networks. Yet this work stagnated in 1969 when Marvin Minsky and Seymour Papert showed that computers did not have sufficient processing power to handle the work required by such artificial neural networks. Then artificial neural networks made a comeback in the form of deep learning when in 2015 AlphaGo, a program developed by Google, was able to beat the world champion in the board game, Go. Go is substantially more complex than chess. For example, at opening there are 20 possible moves in chess but 361 in Go. And it was long believed that computers would never be able to beat humans in this game. AlphaGo achieved its high performance by using a specific type of artificial neural network called deep learning. Today, artificial neural networks and deep learning form the basis of most applications we know under the label of AI. They are the basis of image recognition algorithms used by Facebook, Instagram, speech recognition algorithms that fuel smart speakers and self-driving cars, for example, using Alexa in smart speakers. Then this harvest of the fruits of past statistical advances in the period of AI fall, which we find ourselves in today.